Question 2. A student adds a series of masses to a vertical wire of circular cross-section and measures the extension of the wire produced. This is the force extension graph of the data. Mark on figure 1 point P beyond which Hooke's law is no longer obeyed. So Hooke's law is being obeyed in that straight section there. So as soon as it starts to bend over, you need to mark P there. Part 2. Outline how the student can use these results and other measurements to determine the Young's modulus of the wire. Okay, here goes. So we need the Young's modulus is equal to the stress divided by the strain. So on your formula sheet, it's there. Young's modulus is equal to stress over strain, and that's stress on that strain. So it is F over A, L over delta L. Right, so we need to find the Young's modulus. So we got a force, we have an extension, so we know those two. So I'll just mark those up in a different colour. We know that one and we know that one. So we need to find that one and that one. So let's say that we've done that. So how do we do that? Measure the original length. And it's a good idea in practice to always write down what you would measure something with in any experiment question. It's not a mark for it this time, but it's worth getting into the habit. So we would use a tape measure for that. And measure the diameter. We need the diameter to calculate the area. And we use a micrometer for that. The area is equal to, so it's pi r squared, so that's pi times by r, which is diameter over 2 squared. And then you would pick any two values of f and delta L from the graph, but you have to be in this region here. Okay, so in the straight region, and it's always best to use bigger values, so you put near P, I think. So you want to pick something like that value there. That gives you your delta L. That gives you your force, and then calculate E is equal to FL over A delta L, which is what we started with. And we know all of those. We got that from there, that from there, that from the original length. So I'll just put L there, and that is from there. So the diameter D there. When the wire has been extended to A, where's A? So presumably there. The masses are removed one by one and the extension is remeasured. Draw the shape of the graph that you will obtain. So we've gone beyond the elastic limit here. So you need to draw a line that's going down like this, and you need it to be parallel to that one. So there we go. So that's the unloading curve there. Explain why it has the shape you have drawn. So A is beyond the elastic limit. So the wire will permanently deform. That's probably good for 1 out of 2. The other thing of the shape here is that I said it was parallel to that. Why is that? That's because the forces between the molecules doesn't change. We've just moved a bunch of the molecules about to permanently deform it. So the forces between molecules is the same. So the gradient is the same. So that's explaining the shape of the graph. So it goes down to there. That's your permanent extension there. That distance from where you've marked there to there. The metal wire is used to make a cable 6 millimeters, right, diameter. So let's write down what the radius is straight away. So the radius is going to equal 3.0 millimeters, so that's times 10 to the minus 3 meters. Right, I would advise you always to write values like that down onto your paper as soon as you get to them. The Young's modulus of the metal cable is 2.0 times 10 to the 11 Pascal. Calculate the force necessary to produce a strain of this. Well, the Young's modulus is equal to the stress divided by the strain. So once again, that's the same law that we used last time. This one here. So the stress is the force divided by the area and the strain. So we need to divide that by the strain. So let's just leave the strain at the moment because we're given the strain there. So we need to rearrange this to get force equals something. So force is equal to, move the A up there, and we get A times by E times by, and we're dividing by strain here, so we need to times by it over here. So there we go. Right, R squared, so pi times by 3.0 times 10 to the minus 3 squared, so that's the radius there. Make sure you use the radius, not the diameter. Or you remember to divide it by 2. E is the Young's modulus, so that's 2.0 times 10 to the 11. And the strain is 0.20, and that's a percentage, so we need to divide it by 100. So here's my calculator. And what we're going to do now is type all that in. So we have pi times by, put this bit in brackets, 3 exponent minus 3 all squared times by 2.0 exponent 11 times by 0.2 divided by 100 equals, make it into a real number, and we get 11,309, and this is a force, so that's in newtons. Okay, the mean question asks it for the answer in kilonewtons, so you have to convert that to kilonewtons. Your calculator will do that for you. Just press this ENG button there, and it's gone to 11 kilonewtons. So 11 kilonewtons, and I've put that to two significant figures because that's 2SF, that's 2SF, and that's 2SF, so 2SF. Okay. The cable is used in a crane to lift a mass of 600 kilograms. Determine the maximum acceleration which can be determine the maximum acceleration with which the mass can be lifted if the strain in the cable is not to exceed that. So that's the maximum force then. So let's have a go. So that's the maximum force in the wire, sorry. So draw a little sketch first. Always in these sorts of questions, mechanics questions, always draw a tiny little sketch. It will save you a world of heartache later. So we've got 600 kilograms there. We've got two forces acting, its weight, we've got the tension in the cable, and the thing's accelerating upwards with some acceleration there. And we need to work out what that is. Okay, so Newton's second law, the resultant force is equal to the mass times by the acceleration, but the resultant force is going to equal the one that's going up, take away the one that's going down, so T minus mg like that. Divide through by m, and I get A is equal to T over m minus mg over m, so they cancel. So I've got T over m, take away mg, so that's 11309 divided by 600, take away 9.81, the value for g. So let's try that, shall we? Has it remembered my answer? Yes, it has. So that's the answer to the previous question. Divide it by 600 and we get that value. Take away 9.81 and we get 9.03955 ... Two significant figures. We want 9.0 to SF, like so. Okay, that's 2 part 6. Question 2 part 7. An engineer redesigns the crane to lift twice the load, the same maximum acceleration. So if he's got twice the load, then that's going to increase the force by double. So for the same acceleration, the force must double. Okay, discuss the changes that could be made to the cable of the crane to achieve this without exceeding the same strain. So that has to stay the same. So if the force doubles, we can either change the cross-sectional area or we can change the Young's modulus. We need changing the cross-sectional area seems the easiest. So we can say here to keep the same strain, we can double the cross-section area. Okay, so the easiest way to double the cross-sectional area is to tie 2 strands of the cable together side by side, which is how steel cables are made, with lots and lots of separate strands. We've probably got, what, 2 marks there, because we've made 2 points. So how do we get the 3rd one? Well, I guess we have to talk about this, I don't guess, I know we have to talk about this quantity here. So that's got to stay the same, that's doubled. If we don't change that, we have to change this. So the other way would be to use a material with double the Young's modulus. I mean, that's a bit of a bizarre answer, because if the engineer has built a crane, he's presumably using a particularly strong material here. It's going to be very difficult to find one with double the Young's modulus at a sensible cost. So, but never mind. That is what the physics tells us. The physics tells us that if that stays the same, that stays the same. We can either change that or change that to hold that still. So there we go. That's question 2 completed.